Hi. In a previous video, we introduced the definition of primitive of a function, so a function whose derivative is a given function. We have seen how it works and first examples of primitives for elementary functions. We have seen that not all elementary functions have immediately a primitive. We will see how to compute later in this video and in next videos. Now, let's enlarge a bit our ability of computing primitives. The first remark is to observe that as for derivative, also primitive is a linear operation. Linear is a property that we say when we have an operation that takes a linear combination of objects and says that the operation of the linear combination is the linear combination of the operations. So for example, if we have a linear combination alpha f plus beta g and we differentiate this, the derivative of alpha f plus beta g is alpha derivative of f plus beta derivative of g. The same happens with the primitive. The primitive of a linear combination is the linear combination of primitives. Here, clearly, alpha and beta are constant, so scalars, numbers. Now, we can easily see where this formula comes from, because if we call capital F a primitive for little f, call capital G a primitive for little g, and we want to show that alpha, this capital F plus beta, this capital G, is a primitive for alpha f plus beta g. So we take this alpha capital F plus beta capital G and we differentiate. Because of the linearity of the derivative, this is alpha capital F prime plus beta capital G prime. But these are little f and little g, so we have alpha f plus beta g. Therefore, this function here has derivative, this one. And this means that this is a primitive of this, which is exactly what this formula says. So for example, imagine I have to compute the primitive of e to x plus 3 times sine x. Now, I could decompose by linearity this problem into easier problems, because I can say that the primitive of the sum is the sum of the primitives, and then carry outside constant factors, and therefore say that this is primitive of e to x plus 3 times primitive of sine x. I know primitive of e to x is e to x. I know primitive sine x is minus cosine x, and I get the final answer to this. Of course, this is interesting because it allows to decompose a complex problem into smaller sub-problems. So it helps, but of course it's particularly limited because for the moment we can use this. The idea is that if you want to decompose this in this way, you need to be able to compute these two primitives. So for the moment, they must be just elementary primitives. To enlarge a bit our skill, let's return back on a formula for the primitive of the exponential, for example. Now, the derivative of e to x is e to x means that the primitive of e to x is e to x. What if, instead of x, here we have an expression of x, so a function of x, e to f of x? We may notice that the derivative of this is, by the chain rule, e to fx times the derivative of the argument f prime x. This formula says that e to fx is a function whose derivative is this thing. So in particular, this means that the primitive for this is e to fx, which is written in this formula. So where is the point? If we are able to recognize that our primitive has this shape, we can compute the primitive because this is just e to f of x. Let's see a couple of simple, very simple examples. Here I have e to 2x, just a little modification of e to x. Now, I look at this exponent 2x as my f of x. I don't see f prime here. F prime of x, in fact, is equal to 2. I need a 2 here. I do not have. I can add, or better, I can introduce 2 by multiplying and dividing by 2, for example. Now, I have here e to fx times f prime of x, which is good, but this 1/2 bothers, apparently. Well, actually, what I can do is that I can carry this 1/2 outside of the primitive by linearity, and this now becomes 1/2 this primitive, which is exactly in this form, e to fx times f prime x. And this then is equal to e to fx, so e to 2x times 1/2 that I had before. And the calculation is over. Similarly, here we have a primitive of x e to x squared. Now, when you compute primitive, you have developed some skill in looking carefully at expressions and recognizing derivatives. So, for example, here I see e to x squared. What if I take x squared as fx? The derivative of x squared is 2x. I have x, I have not 2x, but I can do the same as before. I multiply and divide by 2, and then I carry outside this 1/2. So this becomes 1/2 primitive of e to x squared times 2x, which is exactly of this form. So it is 1/2 e to x squared. The same kind of formula can be deduced in all the other cases we have seen for the elementary primitives. For example, I have primitive of an expression like sine of something times the derivative of the argument f of x. Now, here I should recognize that this comes from a derivative. I got this differentiating what? I got this differentiating cosine, hyperbolic cosine of f of x. Because if you differentiate this, you get the derivative of hyperbolic cosine, which is the hyperbolic sine, evaluated in the argument fx, times, because of the chain rule, the derivative of the argument f prime. So this expression here is exactly the derivative of this. Now, what is the primitive of the derivative of something? Now, primitive and derivative are one the inverse operation of the other, so it's like a composition, no? Operation, inverse operation with direct operation. The two kills together, and so what remains is cos of fx. Similarly, I can see primitive of hyperbolic cosine of x times f prime x outside of the argument of hyperbolic cosine, of course, and this is hyperbolic sine of fx. And similar formula for the trigonometric sine and cosine. I invite you to verify this formula by your own. Example. Let's look at this, which is, by the way, an elementary function. So we have not seen, for the moment, a primitive for tangent because we do not have immediately in mind what should be the function such that the derivative of this is tangent. We know what is the derivative of tangent, which is another story. We want a primitive now. Now, tangent is the ratio between sine and cosine. Here, the point is to notice that this numerator is about the derivative of the denominator. To be exactly the derivative, because the derivative of cosine is minus sine, we need the minus. We can introduce this minus multiplying 2 times by minus 1, for example, because minus 1 times minus 1 is 1. And take one of the two minus 1 outside by linearity. So now we have this structure. Minus primitive of minus sine x, which is the derivative of cos x, which is the denominator. This is a very particular structure, f prime over f. Now, if we think about where this could come from, this comes from differentiating log of fx when fx is positive, because if you differentiate log fx, you get 1 over fx times the derivative of the argument f prime x, which is exactly this fraction. But when fx is negative, you could obtain the same by differentiating log of minus fx, as you can easily see. So in a unique word, this is log of absolute value of fx. Therefore, the primitive for the tangent is just minus log of absolute value of cosine x. Nice. Here we have another example. We have this primitive 1 over x root of 1 minus log of x power 2. It could be apparently difficult. Sometimes it's just a question of rewriting things. So you see that if we put the factor 1 over x here at the right alone, 1 over x is the derivative of log of x. And therefore, we may recognize something here, because when do you obtain 1 over root of 1 minus a square? When you differentiate the arc sign. And in fact, if you differentiate arc sine of log x, you get the derivative of arc sine, 1 over the root of 1 minus the square. Square of what? The argument here, which is log x. So you get exactly this fraction here. Then you have to differentiate by the argument of log of the arc sine, so which is log, which is here. And that's why we get arc sine of log x. Well, I hope that this video has been helpful for you, and the suggestion is, of course, to practice with these few first formulas we have discovered in these initial videos. Good job.